Hello. Could someone confirm whether I'm audible?
Yes, sir.
Okay. Hello. This is Algebra 2. I am your instructor. Since I haven't seen you at all in person, maybe I just thought I will. Sorry, it's slightly dark. Okay. Yeah, sorry. Okay. So okay. So this is, let me share my screen. Is the screen visible now?
Yes, sir.
Okay. Yeah. Okay. So this is Algebra 2. It's sort of a continuation of the course that you did last semester. Okay. So so that we are on a familiar ground, we will start with. So maybe about a third of the course will be linear algebra, continuation of the things that you did last semester, and about 2/3 of the course will be group theory. So that probably is new for some of you or many of you. And after that, time permitting, maybe last 2 weeks, we will try to do some linear algebra and group theory together. So that, I mean, that's me. So that is tentative. That really depends on how much time we have at the end of the semester. Okay, so that is the overall plan for the course. Okay, so for most part, I will follow Artin's book, Michael Artin, okay, Algebra, second edition. Okay, so there is some difference between the first edition and second edition. The problem sets are different, and also some other ways. Maybe not the chapters that we will discuss, but some chapters are different. Okay, so I will specifically be using this one. So I think if you try to get the book now, you will get this edition. So first edition has been out of print, I think, for some time. Okay. So that is the thing. And all details about the course, evaluation, etc., they're all in Moodle. So please make sure that you check the Moodle site for this course regularly. So things like, okay. So there is a once a week tutorial session, okay, which will be conducted by the two TAs. They will do it in parallel, okay. So that the details of which group is under which TA, etc., they're all available in Moodle. Okay. And there will be a quiz, weekly quiz, essentially based, or maybe I should say primarily based on the stuff that I covered in the previous week. That will also be online in Moodle. It will be half an hour quiz, but there it will show us 35 minutes. But it is that you will get half an hour to do. But even if you are late by 5 minutes to start because of network correction, you can still get 30 minutes. Okay. So it will say after you start 30 minutes, okay, or the end of the quiz, whichever is earlier. Okay. So if you start at, so it's nominally from 8:30 to 9:05. So if you start at 8:30, you will end at yours will finish at 9 o'clock. And or if you start at 8:35, you can get time till 9:05. But if you start at 8:40, you will still get only time till 9:05. So that is the way it is set up. And and this will be every week except the week of midterm exam and the final exam. Okay? And the quizzes will contribute to some fraction of the grade, 30 or 40. So please check the document. I forget. Okay. Then there will be midterm exam and a final examination, which will cover all the topics. Okay. So that is how the assessment is organized. Okay. And yeah, so please, if you have questions about whatever administrative matters, some problem is not clear in the assignment, etc., feel free to email me. I will be able to, I mean, whatever is feasible, I will try to address it. Okay. Yeah, and in the tutorial sessions, in each session, about 3 or 4 of you, depending on the amount of time, will be expected to present your solutions. So these are problems that are already assigned to you. The TAs will announce in advance who the 3 or 4 people are. Okay, so you should prepare your solution and present it to the class, and this will go so all of, every student will be required to go through this step. Okay, and attendance in the tutorial sessions is mandatory. If you're okay, so it's equally as important as the lectures. Okay, so it is important. Okay, so yeah. Okay, so that is about administrative matters that I wanted to just briefly say, but essentially all information that you need is there in the Moodle page for this course. If something is not clear, please ask. Okay.
So we need to submit solutions as well as we need to send the solutions.
No. You don't need to submit it. That is okay. You will be required to discuss your solution in the tutorial. You don't need to submit it to me.
Okay, sir.
Yeah. There is no need to submit it, but you have to solve it because you will be asked to present your solution. Okay. Yeah. So that is and there's no need to submit it, which is why there's a weekly quiz. It's to make sure that you have understood the topics from the previous week. Right? I mean, that's the essential. So that's yeah. Yeah. So let me then. Are there other questions about administrative matters? Okay, I think most of you responded in that feedback form about what you know about characteristic polynomial and things like that. Okay, so from what I mean, for majority of you, the topics in section 4.5, which is about characteristic polynomial, something about eigenvalues, etc. Most of you, are okay with it. That's what you said. At the same time, 4.6, which is about diagonalization and triangular matrices, that is new or only some vague idea of what is going on. So the way I've planned the initial lectures is I will quickly review the topics from section 4.5, which is they're just a quick review. Okay? And 4.6, I will do it thoroughly. That will be okay. So that's okay. So okay. Yeah. So even after this, if you feel that some topics I have rushed through or I have not, you had not, I use some argument in a proof which has not been proved last semester or something that okay, then please let me know. Okay. So because this is in a sequence, it's a little, I did look at Professor Ramdas's notes, another one he had posted in for his course. So I have a vague idea of what has been covered, and I also talked to him before I started to prepare my lectures. But in case there'll be some point here or there that he missed and I used it without proving it, please alert me. Okay, I will go over those topics also. So that's the. And I will post these online. So this is being hopefully be live streamed. I will send. I forgot to set this up earlier, so I don't have the URL now. But eventually, I'll collect them to a playlist, and then you will be. I'll give you that link to the. I will post the link to the playlist in the Moodle page. Okay, so you can access it from there. Okay. And yeah, I'll also upload these notes. Okay, so that's just about administrative matters. Okay, so this is just a quick review of characteristic polynomial. Okay. So so throughout, by V, so F will denote a field. Okay, typically it is the reals or complex numbers. And V is a finite dimensional vector space over F. Okay, and I hope that you are now familiar with that. If n is the dimension of V as a F vector space, then V is isomorphic to Fn, which is just the set of n by 1 column vectors. Okay, so this I hope you are familiar with this fact. Okay? So, and it is using this that we will often write linear transformations as matrices. Okay? And one of the see, it is easy and sometimes much simpler from the point of view of an instructor to develop linear algebra abstractly. So just say what a field is, what a vector space is, and without worrying about how anything can actually be explained or computed. Okay? But I think Artin's book makes a clever balance of doing the abstract things and simultaneously doing the how to do the computations, how to visualize this using matrices. Okay, so I think so. Therefore, I like that approach. So I will essentially follow Artin's book. As Professor Ramdas did. So that's one reason for this choice of book, because it's also easy to do. It's tedious because you do matrix calculations. To do to teach this purely as the properties of matrices, but then one would not know it well enough abstractly to apply it in various contexts. Okay? So both has. I think so. Therefore, in this book, hopefully, one will learn to see both as one way of just doing the same problem in two different ways. Okay, so this is what we will. Okay, that's okay. So T is a linear transformation from V to V. Okay, so we can think of T as if n is the dimension. So typically, I will just use n to denote an arbitrary dimensional vector space, the dimension of an arbitrary dimensional vector space. Okay, so this will be an n by n matrix. Once you choose a basis, it is an n by n. Okay, once we choose a basis of V, we can express T as an n by n matrix over F, okay, where n is the dimension of U. Okay, so we will use both these things. So now the characteristic polynomial of T is the determinant of Ti minus T, okay, where little t is a variable. Okay, so what does this mean? I here is the identity map from V to V. In other words, a little element V goes to itself. So that is a linear transformation, and it corresponds to the identity matrix in any basis. So whenever we write a matrix for a linear transformation, we have to keep in mind that we are discussing we are discussing that with respect to a basis that may not have been explicitly stated, but it's understood that there is a basis in question. Okay, so when we say, but identity for the identity map, it doesn't matter which basis we choose. In any basis we write, we will get the identity matrix. Okay, so this is I is that. Okay, and so then t times I minus t, little t times I minus t is also a linear transformation, and we can talk about its determinant. And when we talk about its determinant, we're talking about the determinant with respect to of the any matrix representing it. Okay, so if A is a matrix representing T in some basis.
Sir,
Yeah.
is it a fact that IN will always be IN for any basis? Or
Well, it is not. I mean, it is a fact in the sense that it is a statement that can be proved using things that you already know. I am not making a. I'm not stating an axiom. I am stating a. I am making a statement that can be proved by things that you already know.
okay, sir.
Okay. Okay. If you have not, maybe I will add as an exercise. I mean, it is better. Yeah. No. It is important that we check these things. Yes. It is not an axiom. It is a. I mean, it is something that you can prove. Therefore, you should try to prove. I mean, if you have difficulty, I can help, but you should try first.
Okay, sir.
Yeah.
Thank you.
If A is a matrix representing T in some basis, then so we will denote this by P. Maybe. Is it denoted by P? Okay. Then PT of T is determinant of T times identity minus A. Okay. So now it's very concrete. We have a matrix, and we have two matrices, T times identity, and you have another matrix A. Take the difference, compute the determinant. Okay. So this we can expand along one of the rows and then compute this thing. So this is okay. So let us quickly do an example. Okay. Let us say that T is given by the matrix A. Okay. So again, with respect to some basis. Okay. So what exactly that basis is usually not relevant for this question that for computing characteristic polynomial. So the characteristic polynomial of T is determinant of T times the 2 by 2 identity and this is just T minus 1 minus 1 minus 1 and T. Okay, this is T minus 1 times T minus 1. Okay, so so now let's look at what information this this characteristic polynomial. We'll come back to this example in a minute, but let's worry about what information this characteristic polynomial carries. Okay, so the information a polynomial will carry is about its roots. Okay? What are the roots of the polynomial, and what are its multiplicities of the roots? Okay, this will come up in the next few lectures. Okay? But right now we will just worry about roots of PT. Okay? So let's write an observation. Okay? So lambda in F. I'm going to write a sequence of implications. It will become clear in a while where I am heading. Is a root of P. Okay. Let us say that lambda is okay. I mean, I'm taking some lambda. Okay, maybe I should write it properly. Let lambda inside F be in F. Lambda is a root of P of T. Okay. What does this mean? Okay. This just means that, well, that is just what it means. Lambda equals 0. Okay. Which implies, So this itself is the determinant of a matrix. So this just means that determinant of the matrix lambda in minus a is 0. Sorry, t. It doesn't matter which basis we choose. Okay. So then I should not write in. Let me just write I means the identity map on V. Okay. So lambda I times is 0. Okay. So now from what I understood, you have seen, if you have a square matrix whose determinant is 0, it means that its null space is non-trivial. Okay. So it's not an invertible matrix. So if this thing that I'm going to write now, if it has not been discussed in your algebra 1, I'm reasonably sure it would be, but I just let me know, or you should discuss it in the tutorial if you don't understand. I mean, this part. Okay. Lambda it is not an invertible matrix, not an invertible linear transformation. Okay. Which implies that there exists a non-zero vector V inside V, okay, such that lambda I minus t V is 0. Okay, that is just saying its null space is non-trivial. Kernel, or I don't know what word you would have used. Kernel, sometimes, I mean, different authors use different terms. It's called kernel or null space. So that is this is non-trivial. Which, but what does this mean? This just means that there exists a non-zero vector V in V such that lambda times I times V, which is just lambda V, that is equal to TV. Okay, which now implies that lambda is an eigenvalue of t, okay, and V is an eigenvector of, I mean, this V in the previous step is an eigenvector of t for lambda. Okay, I mean, okay, eigenvector means it has to correspond to an eigenvalue. It is associated to an eigenvalue, and this is that. Okay? So this is sorry, let me just zoom it out so that I can see. Okay, so this is just what it means to say that lambda is the root of the characteristic polynomial. Okay, so it means this, that there exists a non-zero vector with this property. That is exactly saying lambda is an eigenvalue. And if you think about it, the converse directions are also true. If lambda is an eigenvalue, then there must exist a non-zero vector with this property. Okay? That is just saying lambda I minus t times v is 0, which is just saying that this is not an invertible linear transformation, which is just saying that the determinant is 0. That is saying this. Okay, so the roots of the characteristic polynomial are exactly the eigenvalues of t. And once we understand the eigenvalues, then we can try to solve the linear equation to find eigenvectors. Okay. If lambda is an eigenvalue, write down lambda I times t as a matrix, solve using Gaussian elimination or anything, whatever method we have, and find non-zero solutions to that equation, lambda I times v times lambda I time minus v times some v is 0. Find non-zero v satisfying that, and that those would be the eigenvectors. So this is the idea. Okay. I mean, this is what it means. Okay. So in the example, what was the so in the example, pt of t was t minus 1, t minus 1. Okay, so it's easy to check the following. When one can see that it has two real roots. Lambda is a root of this if and only if lambda and lambda minus 1 are multiplicative inverses of each other. That's what this condition says, right? So one can check that p of minus 2 is positive, p of minus 1 is negative, p of 0 is negative. And these are sorry, that is not what I got it wrong. P of 1 is negative, minus p of 2 is positive, p of 1 is negative, p of 0 is negative, and p of minus 1 is it will be minus 2 times minus 1. This is 2. This is also positive. Okay. Yeah. Okay. So therefore, there are two roots by intermediate value theorem. So they okay. So there are. So this has. Therefore, T has two real eigenvalues. Okay. And one can find their eigenvectors. Okay. So just to step back and ask, why do we care about knowing any of these things? Or so at least characteristic polynomial, we can think of it as a way of telling us what the eigenvalues are, and hopefully with that information one can also calculate the eigenvectors, and we will see why that is useful. Okay. So let us just briefly ask, okay, why are we concerned about this eigen stuff? Eigenvalues, eigenvectors, eigenspace. Okay. So the first, I should not say first. The most basic observation, which we know from the definition itself, if V inside V but not 0 is an eigenvector of T, then eigenvector of T, then TV is a scale. TV is a scalar multiple of V. Okay. So this is, we know TV equals lambda V. Okay. So in other words, if we write V1, okay, for the span, so one piece of notation that I don't know if you used is this. So by this I mean the linear span of V. Okay. So there could be multiple vectors also. I will denote it by angle brackets. Okay. And to say that I'm taking linear span. And if I want to specify what field the scalars are coming from, I will also write the field. Okay. So here there's only one field that we're discussing, so it doesn't really matter. Okay. So this is just notation. If you if you're not seen it, I'm going to use this sort of consistently throughout. This angle brackets to denote linear span. Okay. So TV is a scalar multiple. So if you write V1 as this, so if we okay, sorry, since I wrote this, if maybe I should not write denote. The linear span of V by V1. Okay. Then for any V inside V1, TV1 equals TV1 is TV is inside V1. In other words, as far as if you're thinking about T as functions from V to itself, this subset V1, which is a subspace, is actually sort of stable under that thing, meaning elements of V1 only go to elements of V1. They don't go outside. Okay, so this is a so in some sense, eigenspaces identify this property. If you have an eigenvector and you look at its span, it is just a scaling. Okay, so each ray is just scaled. Vectors lying on a ray are just scaled on the same ray. So this is one. It is just reinterpreting what we know. It is not some new information. It is just reinterpreting things. Okay, so this is one. Okay, so and this will become. Will be useful. Okay, that's the first.
If angular bracket V is the F denoting the field F or
correct. Yeah. So here okay, maybe I should. Sorry. Thanks for asking. Maybe I should say. So okay, so it's just an aside. Frequently, I will use to denote linear span. Okay, so specifically, so let W be a subset of V, okay, by F angle brackets W, or sometimes if it's only finitely many elements, we'll just list those elements and not actually as a set. Okay? F W, we mean the subspace, the linear span of elements of W, okay, where the scalars come from F. Okay, so typically, we see sometimes when we think about complex vector spaces, they're also real vector spaces. A one-dimensional complex vector space is a two-dimensional real space. Okay? An n-dimensional complex vector space is a 2n-dimensional real vector space. So sometimes for those things, we may have to switch between. We may not. We meaning in this course, we need not. We might not need to. But I cannot. I can't say that for sure now. Okay? But in case so the same set can be thought of as a complex vector space or a real vector space. So in that case, we'll have to specify when we are taking linear spans of elements, are we taking complex linear spans or real span? So just to specify that, we will write F here. Okay. So what does this mean? Okay. That is the set, okay, alpha 1 W1 plus some alpha m Wm, where m is a natural number. Okay. Alpha i's. So m is all possible m's, but finite. That is it. Okay. Alpha i's are in F for all I. For all I 1 less than I less than m. And Wi are in F, are in W, okay, for all 1 less than I less than m. So when we say linear span, we mean only finite linear sums. Okay. So W itself may be infinite, but we take all possible finite subsets of it, all possible scalars, coefficients for it, and then take the sum. We multiply the scalars and take the sum. Okay. That's what we mean by linear span. So this thing we will just abbreviate it as F angle brackets W. Okay. Sometimes F will be clear from the context, then I might omit F, but it will be clear. Okay, so that's just a notation. Okay, so just to make sure that we are on the same page as far as notation is concerned. Okay, Okay, so this is the first thing, that if you take an eigenvector and look at the linear span of that eigenvector, that's a linear span of some subset is going to be a subspace. That subspace, I mean, as a set is fixed by T. T takes elements from V1 to inside V1. Elements of V1 don't go outside. I mean, under the function T. Okay, so that's the reason why. I mean, okay, I should not say that's the reason. That's one property that will sort of come up when we start discussing diagonalization. But again, as I said, it is not a new property. That this is rehashing what we knew. Okay, so that's other. Okay. Yeah. Now the second thing is, so let lambda be an eigenvalue. Okay. We can look at this V lambda, V inside V, such that okay, V is an eigenvector of T for lambda, corresponding to the eigen union 0. I mean, 0 by definition is not considered an eigenvector. So when we consider only eigenvectors, we will not get 0. So take 0 also. Okay. So let this be. So this is going to be a subset of V. This is a subspace. So there is an assertion here. I'm defining it as a subset of V, and I'm asserting that it is actually a subspace. So that's okay. So we'll see the argument in a minute. Okay. So this is an important property, which is that the collection of eigenvectors for given eigenvalue is a subspace of this thing. Okay. Okay. So proof. Okay. I mean, the proof is proof of this second point. Okay. So what do we have to check? We have to check that this is closed under linear combinations. But linear combinations means we have to take finitely many elements from here and then apply scalars and then take the sum. Okay. And such a thing, if you apply T, it would just be scaling by lambda. That's what is being asserted. Okay. A linear combination of eigenvectors for the same eigenvalue is also an eigenvector for that eigenvalue. In other words, that's what is okay. Okay. So let V1 through Vm be inside V lambda. Okay. And alpha 1 through alpha m be inside F. Then T of alpha I Vi. Okay. T is linear, so we can take it inside. T is linear, so you can take scalars outside and also sums outside. So this is just alpha I T of Vi. Okay. But yeah, alpha I lambda Vi. Okay. And that is just lambda times this thing. Okay. So therefore, this is a okay, is 0 or is an eigenvector of T for lambda. Okay. I mean, we're not saying that this linear combination is non-zero. If it is non-zero, it's an eigenvector. Okay. So therefore, in other words, it belongs to V lambda. So that is the proof of this earlier assertion. Okay, so this is a subspace, and this is a okay. So this is so these ideas will be used when we want to build this idea about diagonalization. So which is why perhaps you've seen parts of this last semester, but so maybe it is a review for you, maybe it is not, but it is important that we collect these things before we start discussing diagonalization. Okay. So next is I will state a important property about eigenvectors corresponding to distinct eigenvalues. Okay, so I will state it in a weak version, which is just to illustrate the point, but we will prove it properly before we use it. So here is so this is just to get a feel for that thing. Okay, if V1 and V2 are eigenvectors of T, for eigenvalues lambda 1, lambda 2 respectively, okay. V1 for lambda 1, V2 for lambda 2, and they're distinct. Okay. Then V1 and V2 are linearly independent. Okay, I mean this is a property about. I mean, you can make the statement about any number of eigenvalues. I mean, any number of eigenvectors. The statement is about distinct eigenvectors. So if you have R distinct eigenvectors, lambda 1 through lambda R, for each lambda I, choose a Vi, which is an eigenvector for that thing, then those V1 through VR would be linearly independent. Okay, it is true for more than two vectors also, but it is just I just want to use this now so that we just get a feel for the argument. We'll prove it properly in the general version that we know that we need. Okay. So by way of contradiction, so this, I'm just proving this. Okay. Assume that there exists alpha, beta inside F, alpha not equal to 0, beta not equal to 0, such that alpha V1 plus beta V2 is 0. Okay, so assume by way of contradiction that V1 and V2 are not linearly dependent. So okay, yeah. Okay, so then let us apply T to this one. Okay. This would imply that T of alpha V1 plus beta V2 is 0. But what is T of alpha V1 plus beta V2? This is alpha lambda 1 V1 plus beta lambda 2 V2. Okay. This is also, this is 0. Okay. But from the first equation, okay, from 1, we get alpha lambda 1 V1 plus beta lambda 1 V1 equals 0. This is from 1. Okay. So together we get that beta times lambda 2 minus lambda 1 times V1 is 0. Okay. This would imply that, so V1 is non-zero. It's an eigenvector, not V1, V2. Okay. V2 is non-zero, it's an eigenvector. Okay. Beta is 0 or lambda 2 equals lambda 1, which is a contradiction. Okay. Because if beta is 0, then I mean, this would not have been a. Yeah, okay. So this would not have been linearly. I mean, linearly dependent to start. I mean that because we assumed. Okay. So this is the end of this. Okay. So this is argument. So these are three ideas about eigenvalues and eigenvectors that will be used sort of I mean, sort of seriously, or
So,
this is the yeah.
so we could have alpha not equal to 0, but beta equal to 0.
No, that would just say alpha v1 is 0, right?
Okay, sir. Yeah.
So I agree. I mean, for two vectors, it's slightly misleading because when we say linearly independent, we mean some coefficient is non-zero. I agree. But if there are only two vectors and one coefficient is 0, the other one coefficient is non-zero, then that vector itself has to be 0, right? Yeah. So it's yeah, I agree. But as I said, we will do the general case. Not this lecture, but maybe on Thursday itself. Okay. I mean, soon, the way once we start discussing diagonalization. But so this is the sort of, I mean, so yeah, so this is the key, sort of idea behind diagonalization, that we would like to decompose V. We would like to get a basis for V, okay, so that the basis comes from eigenspaces. These are okay, and therefore T just acts by scalar multiplication. It'll become clear. This is just okay. So we will use these things, but we don't. Okay, the details will work out when we get there. Okay. Okay. So today I will just do triangular forms, not diagonalization, and then we will take up from there. We will prove the general version of this lemma in the next lecture. From there, we will start discussing diagonalization. Jordan canonical. So the first, we will do Jordan canonical form. That's the first topic that we're doing. I mean, so all of this preliminary discussion is to build to that one. Okay. That's the first thing. Second, so that's okay. Maybe it'll take us 3-4 lectures. The second thing is 3 lectures, maybe not 4. Okay. Second topic that we would like to do is the Cayley-Hamilton theorem, okay, which says that every matrix satisfies its own characteristic polynomial. Of course, we have to write down what it means, but okay. So that's the thing. And so this is, and after that, we will start discussing bilinear forms. This. Professor Ramdas told me that you had seen, I mean, he had discussed some things with you last semester, but due to lack of time, he did only some of them without proof, only the basic things, and some of them without proofs. So we now in this semester, we have time, so we will do them in greater detail. So in linear algebra, those are the first 3 topics. First, Jordan canonical form, then Cayley-Hamilton theorem. And the next one is a little long. It's a whole chapter in Arjun's book. We will do substantial part of it, at least the key results in it. Maybe not everything. Not maybe, of course not everything, but the key results in that thing we will do. Then we will go to group 3. Okay, so now we'll write triangular form of linear transformation. Okay. So what we want is, given a linear transformation, is there a basis with respect to which it looks like a triangular matrix? Okay. What is the advantage of triangular matrices? See, for most calculations, it's actually easier to handle matrices that have lots of zeros. See, there is of course the abstract reasoning about linear algebra, matrices, linear transformations, and what it means, etc., etc. But there is also the very concrete parts of linear algebra, which is the part of mathematics that is most applied in any. So not just for abstract reasoning, but one also needs to. Not in this course, but not. And neither am I would know much about it anyway. But in thing that how can we effectively do calculations, because lots of things depend. A lot of engineering and sciences depend on being able to compute with matrices. Okay, so it would be nice to have, if you have a linear transformation, that is useful. Yeah, that's useful in some context. It'll be nice to know if it has a matrix form which has lots of zeros in it. Then computations will become quite simple. Okay, so that's you can see that as a motivation. Okay, so the question is, given a linear transformation, T from V to V, okay, is there a basis of V with respect to which T, the matrix of T, is, I mean, I should not say the matrix. T has a triangular matrix. Okay, so we can think of this as a pre-version of asking for a diagonal matrix. Asking for a diagonal matrix will be stronger than this because diagonal matrices are triangular. They're both upper triangular and lower triangular. So here, at least when I say now, I will mean upper triangular. Okay, but after this, we can immediately see how to do it for lower triangular also. Okay, so that's what we want to understand.
When we are just applying a matrix on a vector, we have those elementary row operations. So a triangular matrix should be given.
No. There is a difference. Elementary row operations might change the linear transformation.
Okay.
But here we are asking for a basis for which it is, with respect to which, see, the matrix T has so maybe let me, okay, maybe instead of saying this, instead of waving my hands in front of the camera, maybe yeah. Let me just, okay, so this is just an aside. Okay, so the question is, why not use Gaussian elimination? That's what you're saying, row echelon form, row operations.
Yes.
Wait, yes, it is a, okay. So let's ask, okay. So let us say that we have T from R2 to R2 is given by, okay. So we will use E1, E2 for the standard basis. Okay, so this is sort of a standard notation. Okay, if you take Rn as column vectors, then E1 denotes the column vector with 1 at the first position, E2 at the second position, and so on. Okay. So let us say, sorry, I am working this out on the fly. So maybe this is not the best approach to things. E1, so I want to, E1 goes to E1 plus E2. Okay, and E2 goes to E. Okay, so this I'm not entirely sure whether this is okay. So then, with respect to this basis,
excuse me, sir.
yeah.
Can you please scroll up a bit?
Yeah, sorry, change the page as well. Yeah.
Thank you, sir.
Yeah, I agree. This may not be the right example, but because I'm just thinking about it on the fly. But let me just still try. Maybe I should not try this in an online class. But with respect to E1, E2, the matrix of T is, so E1 goes to E1 plus E2. So it is just 1, 1. E2 goes to 0 times E1 plus this. Okay. Row operations will give the matrix. So I'm just going to subtract the first row from the second row. I mean, second row minus first row. Okay.
Sir, but it is already triangular, right?
No. Well, okay, when we say triangular, we mean upper or lower triangular. I mean, the main diagonal about or main diagonal.
Oh,
and
okay.
things about,
okay.
Yes, we don't,
Okay.
yes. No, but yeah, I mean, that is okay. I could have just put something else here. Right? mean that for the purpose of this example, I don't think whether we have a 0 there or nothing, that doesn't matter. Okay, but what does this matrix represent? I mean, what? Okay, so if
the
you're using
identity
same,
transformation.
yes, if you're using the same basis, it is sending E1 to E1 and E2 to E2, but that's not what we started with, right? So this is not the question. Okay, so yeah, yeah. So this is maybe I should put an exercise to say what is. I mean, as far as basis is concerned, what is maybe I'll just put too many problems for this week, so I will. Okay, but this is not T. Let me just say this: this is not T.
Yes, sir.
I hope that is clear.
Yes, yes.
With respect to the basis. Okay, maybe I can just quickly say why this is not the correct answer with respect to the basis E1, E2. Okay. So maybe maybe I should just quickly say instead of putting this in Excel. See what did we do? What is what we I mean in this row operation, Gaussian elimination, this whole topic. What is that we're trying to do? We're trying to solve an equation. Or in other words, we have a function from R2, which I will denote by X, a function T to R2, which I denote by Y, because I want to refer to these two by different names. Okay, it is just, okay. Now we are asking whether this thing has a solution or not. I mean the homogeneous equation. Okay? In other words, is there any vector in T inverse of 0? That's what we're asking. We have a function from X to Y, okay? And so row operations, echelon form, Gaussian elimination. This whole thing Gauss-Jordan, whatever, etc. Okay, answer or our techniques we use to answer the following question. The question. Okay, what is T inverse of 0? This is the 0 vector in Y. Okay, so think of this as a function. We're looking at the pre-image of the point 0 in Y. That's what we're asking. Okay, but what does this row operation do? What it does is to rewrite a basis for Y. That is not expressing T as a matrix. Okay, so row operations rewrite a basis of Y suitably. Similarly, column operations will rewrite a basis for X suitably. Okay, that's what it is doing. Okay, in a way that is computationally easy. But this is not same thing as expressing Y. I mean, in this situation, I mean, when we do row operations, we are not conscious about it, but we are only changing basis for Y. But when we say with respect to a basis, what does T look? We are changing. I mean, X and Y are the same, and we are doing the same change of basis on both. So there's a slight conceptual difference between asking to write the matrix for a linear transformation with respect to a basis, okay, as opposed to asking to solve. I mean, do this Gaussian elimination on this, or do row operations on this matrix. Okay, so this is just to. I mean, okay. If I'm just mumbling things, just ignore this. But I hope at least you get that this is not what we need to do. Okay, right. This is not, yeah. Okay, so now let's come to the. Okay, maybe actually I won't prove the theorem in 10 minutes or 15 minutes. I should probably not rush. Okay, yeah. So let's come back to this question. So now. So what we are asking is, so T is a linear transformation from V to V. Is there a basis B? Okay, so let us just call it V1 through Vn. Okay, with respect to which the matrix of T is diagonal, is triangular. Okay, so this by mean I mean upper or lower triangular, upper or lower triangular. Okay, but that means, as I said, above the main diagonal, I mean that the main diagonal and above it, or main diagonal and below it. Okay, but not on both sides of the main diagonal. Okay, so suppose it is so. So let us understand. Let's ask. Okay, so how do we write the matrix? The first column will be what is B of V1, T of V1. Okay, so the matrix. So let us say A is the matrix. Okay, so what are the entries of A? First column. I mean, so if you just write A, say A is Aij. So I in this index is the rows, J index is the columns. Usual notation. I'm not changing those things. Okay. Okay. So then, what does this mean? So this means that T of V1 is the first column of A. I should just put it in quotes. But what does this mean? This just means A, first column, right? A I1 Vi. T of V1 is this. Okay. T of V2 is A I2 Vi. So this is not. Okay, this is not the way we are writing V1 V2. Okay, so we are writing V1 V2 in. I mean, we are expressing V2 with respect to that basis. That would look like the column vector E2. Okay. And then we have this matrix A. When we multiply E2, we now actual matrix multiplication, we will get the column vector that corresponds to T of V2 and so on. Okay, so this is how, remember, the matrix is written. Okay. Yeah, so now we have this thing. So we are asking whether, okay, so let's ask for upper triangular. It's just easier to write down. Okay, I mean okay. So suppose A is upper triangular. Okay, so what does that mean? This means that T of V1 is A11 V1. Right? The other things, I mean, for I greater than 1, the things that lie below the diagonal on column 1, they're all 0. So T V1 is A11 V1. That's what it means. So if A is upper triangular, so if T is a diagonal matrix with respect to this basis B, then V1 must be an eigenvector. Okay, and A11 is the corresponding eigenvalue. So that is the observation. Okay, so that is V1 is an eigenvector of T, and the corresponding eigenvalue, I should not say corresponding because it's not one-to-one, associated eigenvalue is A11. So actually it says that there is not much choice in choosing A11. Once we identify which eigenvector we have to use as V1, A11 is already fixed. It has to be the corresponding eigenvalue. Okay, so this is an observation that we want to make. Okay, so that is if there is a basis with respect to which the matrix is upper triangular, then the first vector must be an eigenvector. Second vector onwards, we do not know, but this is the, okay. So therefore, if you want to prove that some matrix has, I mean, if you want to find a basis with respect to which it is upper triangular, then we have to first look for an eigenvector. Okay. Let us just quickly look at what happens when, yeah, so what if it's A is lower triangular? Okay, so suppose A is lower triangular. This means that the last column, there's only one non-zero, I mean, at most one non-zero entry, which is the diagonal entry in the last column. Okay, so this is just says AIN is 0 for all I less than n. This now means that TVN is ANNBN. So either way, okay, if you want to find a basis with respect to which it is triangular, choose whichever one you like, upper or lower, we have to identify a eigenvector. Okay? That is the thing. So let us just note that. Okay? So either way, we need to find an eigenvector of P. Okay. So to find an eigenvector, okay, there is abstractly, there's only one way we, I mean, yeah, we ask if there's an eigenvalue. For that, there's only one way. I mean, okay, I should not say one, there is only one way. Okay. The one way that we know is we can write down the characteristic polynomial. Take any basis. Okay. We are looking for this B, but we can start with any basis we want and write down the characteristic polynomial. Okay. And then we ask what are the eigenvalues, and with respect to that basis, what are the eigenvectors? I mean, what are the eigenvectors? Okay, and that is okay. Okay. So that's the first. That would be what is required. Okay. So therefore, let me state the theorem, and I will tell you why. I'm not going to finish the proof because while discussing the proof, I want to just, I mean, because you're first year, you're probably only beginning to see proofs like what I'm going to do now. I mean, do in the next lecture. I want to just take a 5-minute detour into induction. Often we'll write by saying by induction something is true. Okay, what exactly do we mean by that? I mean, you would have done this in 12th for sure, or 11th for sure, or even earlier. Okay, but that's typically not the way we would write in college. We'll just write by induction something is true. By induction, some property is true for a vector space. So what does that mean? Okay, so that because you may not have, or even if you've seen it in the last semester, it's good to go over that point just once. So because I would need some 5 minutes or 5 to 10 minutes to do that, I will not give the proof. But I will just state the theorem, and I will just say, okay, let T. So now we are assuming F is equal to C. Okay, so let V be a finite dimensional vector space. So throughout, I'm just going to write FBDS to denote finite dimensional vector space. I mean, we have to write that a lot, and lots of takes a lot of time to write. Right? Okay. Vector space over C. Okay. Then there exists a basis of V such that the matrix of T. Sorry. This. So what happened? Oops. Okay. Let T from V to V be a linear transformation. Okay. Then there exists a basis of V, basis B of V with respect to which T has a triangular matrix. Okay. Okay. So what is the okay? So as we observed earlier, to start this thing, to get the corner, the end of the diagonal, whether you're looking at upper triangular or lower triangular, we need to get an eigenvector. Okay. So this is the proof I'm going to do later. I mean, in the next lecture. But okay, so let us say, okay, say we want to show an upper triangular matrix. Okay, so this is just a remark. Okay, suppose we want B with respect to which, okay, T has an upper triangular matrix. Okay, then what do we do? Okay, so we need to first get an eigenvector of T. Okay, so the reason why we can get that is, let P the characteristic polynomial of T. Okay, so then since we are over C, then Pt of T has a root in C. Okay. So let's call this thing lambda. Okay. Therefore, lambda is an eigenvector. Okay. Let V1. So we have found one vector that can go sit as a first vector of the basis. Be an eigenvalue for lambda. Okay. So this is V1. So now, of course, the question is, how can we find V2 and V3 and so on? Okay. And so that we will do. So we will do that by induction. So I'll clarify what we mean by saying in such proofs, when we say by induction, we will do something. Okay. So I will do that. I mean, in the course of the proof, I will explain that by taking a slight detour. Okay. So I will redo I will start from the statement of the theorem and give the full proof in the next lecture. Okay.
I think lambda is a eigenvalue and lambda V1.
Oh, sorry, I got both. Sorry, thank you. Lambda is an eigenvalue and V is an eigen vector for lambda. Okay, thank you. Okay. So I'll stop here. We will please read the lectures and please also read along the book, and we'll continue next.